we know the speed of light, or any other kind of EMR for that matter, is in a vacuum 3.0 times 10 to the 8 meters per second. But how do we know that? There's been hundreds of experiments performed through the years to determine the speed of light. We're going to look at two different experiments, one that gave us a very poor value or very inaccurate value for the speed of light, and one that gave us a much better or much more accurate value for the speed of light. The first one we're going to look at was performed by Galileo. Galileo did an experiment where he had two hills about 1 kilometer apart, with two lanterns, one on each hill. So here's a lantern on the first hill, although it's covered up, so you can't see the light coming from it. Here's another lantern on the second hill. It's covered up as well, so you can't see the light coming from it either. Galileo is on the first hill with the first covered lantern. His assistant is on the second hill with the second covered lantern. He's got some kind of crude timing device. We'll call it a stopwatch, but it wouldn't have been nearly as precise as a stopwatch. Galileo uncovers his lantern so that the light is exposed. At the same time, he starts his stopwatch. The time starts flowing. The light travels towards the second hill. When Galileo's assistant sees that light, he uncovers his lantern. That light travels back towards Galileo. So start your stopwatch when you uncover your own lantern. Stop it when you see the light coming back from the second lantern. If you can time how long it took for that light to travel that distance, and you know the distance, then it should be really easy to determine the speed of light. We would say it's 2 kilometers divided by the time that Galileo measured. What's the problem with that, though? What's the problem with this? Yeah?
The light would get there in like under a second.
Yeah. Exactly. The human reaction time is astronomical compared with the time that it takes the light to travel that 2 kilometers. Light travels, we now know, he wouldn't have known at the time, but we now know light to travel at about 1 billion kilometers per hour. If you had a flashlight in Halifax, a mirror in Vancouver, and then another mirror back in Halifax, and assuming that light could travel from a flashlight from Halifax to Vancouver, back again, and so on, assuming it could do that, and it couldn't do that for a number of reasons, but let's pretend for a second that it could, it would make about 30 return trips, Halifax to Vancouver and back to Halifax again, about 30 of those return trips in 1 second. That's how fast light travels. The amount of time that it would take to travel 2 kilometers is ridiculously small compared to the human reaction error involved in this experiment. Even if we did get a value that was close to the currently accepted value, it would be purely by coincidence, not by any kind of good experimental design. This doesn't work because of human reaction time. It's bad results because of human reaction. We're slow. Okay, we're slow, at least compared to how fast light travels. What's a better way to measure the speed of light? Well, there's lots of better ways to measure the speed of light, but we're going to look at one experiment performed by a guy named Michelson. Michelson also used 2 hills, but these hills are 35 kilometers apart as opposed to 1 kilometer apart. Now, that doesn't make a huge difference because light still travels ridiculously fast, and you could, I mean, there's no way you could stand on top of one hill and use a stopwatch to measure how long it took the light to travel 35 or 70 kilometers. But it's better. Okay, the 2 hills are 35 kilometers apart. We have Mount St. Wilson, again, 35 kilometers down the way, we have this Mount San Antonio. If we shine light from Mount Wilson onto this octagonal-shaped mirror also on Mount Wilson. This mirror is, it's like a stop sign with a mirror on the face, on each of the faces of that stop sign. If we shine light from this light bulb or candle or whatever it is, let's say towards face 4, it will reflect off of face 4, come down here, bounce off of this mirror on Mount San Antonio. Sometimes you see it as a straight mirror, sometimes you see it as a curved mirror, it doesn't really matter. Reflects off of this mirror on Mount San Antonio, bounces back off of side 6, and then reflects into an observer's eye. We haven't measured anything yet, but it's the start. Now what I want to do is start rotating the mirror. So the mirror will rotate on an axis. We can control how fast it spins. We make it go 50 cycles per second, 500 cycles per second, 1,000 cycles per second. We can cause it to speed up or slow down if we need to. We start it rotating. Let's say that this light travels to side 4, bounces off of side 4 down here to Mount San Antonio. But because this mirror is rotating, by the time the light reflects off of the mirror at Mount San Antonio and back to side 6 is in a different position, causing the light to reflect up here somewhere. It doesn't get observed or it doesn't get detected. Does that make sense? It's rotating now, so the reflection angle isn't right to make it observed by this observer. So what do? Like, you could see the light, this observer could see the light when the mirror wasn't moving. We started it spinning, we can't see it anymore. Let's speed it up. Let's crank up the frequency of it a little bit. Okay, at this frequency, can't observe the light. Let's crank the frequency up a little bit. Watch what happens if instead of rotating that much during the time that it took the light to travel from here to here to here, the green section, let's see what would happen if the mirror rotated this much. All of a sudden now, the light comes back and reflects at the right angle to get observed. So it reflected off of side 4, and then as it rotated, the light went down to Mount San Antonio, came back up here, and reflected off of side 5 that at that point was in the right position to cause the light to be reflected to the observer. Does that make sense? So understand what's going on here now. If we know the frequency of this rotating mirror, and that was relatively easy to control, then we can determine how long it took for the light to travel this green section here, from here to here and back again. If we know how much time it took to travel that distance, and we know the distance, then we can use v equals d over t to solve for the speed. We get a much, much better value for the speed of light this way. How come? Why? Like, we're using a distance that's bigger, right? 35 times bigger, but that's not the big reason. What makes this way more accurate than Galileo's experiment? Good, you're not relying on human reaction time. Now, are you going to have the exact frequency of the rotating mirror? Probably not. There's going to be experimental error in that. The exact distance, yeah, maybe you're off by a couple meters in your distance. Okay, but if you're off by, let's say your frequency of rotating mirror is 500 hertz, and you call it 470 instead of 500, and the distance is 35 kilometers, and you make it 34.9 kilometers. Like, you're still going to get a pretty darn good value for the speed of light, because you're not off by millions of percent like you are with Galileo's experiment. You're off by single-digit percent in this one. All right, this is a big deal. We often see mathematical questions where we have to solve for the speed of light using data from a Michelson experiment. We're going to show you an example right now. I'm going to walk you through the recipe, and it really is a recipe for solving these problems. that's going to allow you to solve any of the problems that you're going to see, well, in the worksheet that you're going to work on in a few minutes, and also any test question that you're going to see down the road. Here's the first one. It says a set of eight rotating mirrors in a Michelson experiment rotates at a frequency of 600 hertz. Usually, our frequency is in that 10 to the 2 range, 5, 6, 700 hertz. Usually, not always, usually. So if you're solving for frequency, okay, you can probably expect somewhere in that 10 to the 2 hertz. Right, Carly? The rotating mirrors are placed 35 kilometers from a curved mirror on a second hill. Kilometers, we don't want that. We want to determine the speed of light. Please, the first thing you could do when you see any of these Michelson questions is write down these two equations. Every single time, blindly write down those two equations. V stands for speed of light. D is the distance traveled, which in this case would be not 35 kilometers, but what would it be? 70 kilometers, because it's there and back, right? The time that it took the light to go there and back. T stands for, little t would stand for time. What time? The time for the light to go there and back, which would be the time for 1/8 of a rotation of the mirror, right? Like, let's look back at the picture here again. During the time that it took the light to go from here to here and back to here, side 5, which was right here, rotated 1/8 of a rotation to go right there. So little t, we would say, would be the time for 1/8 of a rotation. Or 1/10 or 1/12. Sometimes you see a question where there's a 12-sided mirror or a 10-sided mirror. Okay? Time for 1/8 or 1/10 or 1/12 or whatever. What does F stand for? Frequency. What does big T stand for? What is it? Nick? No, I thought you were saying it there. Big T stands for the period, which is the time for one complete rotation or revolution, whatever you want to call it. Sub in some numbers. Get something. Let me tell you this. When you solve for something, the first thing that's going to pop out of it is going to either be little t or big T. That's always the first thing you're going to solve for, either little t or big T. And let me tell you this. If you get little t, it's not the one you want. You want big T. If you get big T, it's not the one you want. You want little t. It's one of those grass is always greener on the other side of the fence. You always want what you don't have. If you get little t, you want big T. If you get big T, you want little t. But we can convert pretty easily here. Let's do that as we work through this specific question here. We're looking for the speed of light, so we don't know what that is. The distance we do know, somebody said before, I think it was Isaiah, it's 70,000 meters. The distance there and back. The distance that the light traveled from the 8-sided mirror to Mount San Antonio and back to the 8-sided mirror. We don't know what the time is. Okay, that wasn't very helpful. Two unknowns. Let's go to the other equation. What's big T? Don't know what big T is. What's F? Oh, we do know what that is. It's 600 hertz. So big T, the time for one complete rotation, is 1 divided by 600, which is 0.00166667 seconds. Remember what we said a minute ago? You're always going to get either big T or little t, and it's the opposite of the one you want. We just got the time for one complete rotation. We want the time for 1/8 of a rotation. So what do? Divide by 8. Divide by 8 to get little t. When we do that, we get 2.0833 times 10 to the negative 4 seconds. Now, if you happen to have solved for a little t first, then remember you want big T. How would you get big T from little t? Multiply by 8. If you got the time for 1/8 of rotation, multiply by 8 to get the time for one complete rotation. Let's sub that back into here now. We got 70,000 meters divided by 2.0833 times 10 to the negative 4 seconds. Do the math here. we get 3.36 times 10 to the 8 meters per second. Now that's fast, right? The real speed of light is 3 times 10 to the 8. Like, this is like experimental data, right? You guys know that from your own experiments that sometimes experimental data doesn't really work out the way it should. But it's close. Seems reasonable, right? When the accepted value is 3 times 10 to the 8, we're about 10% off. Which is pretty close to saying, with our criteria we use in our experiments, that it would be verified, right? You're going to have 3 questions to work on in just a moment here. And all 3 of those questions, I want you to not skip steps. Write down these 2 equations every single time. Every single time. Solve for either little t or big T. Get the other one by multiplying or dividing by 8, and then solve for what you're looking for. Questions that I want you to work on are on worksheet number 14, and there are only 3 of them. So you got a good chance to get those finished up in class here, and even getting onto your practice question set that's also due tomorrow.